Your smartphone seen through the genius of Einstein, the quantum eraser experiment. Our premise is that we have a new civilization based on these smartphones. If Einstein were investigating nature today, he would start with what he finds inside your smartphone. Einstein says, "Jeff, you've been telling us that the quantum world is not strange and in fact not different than the world of everyday experience except for size. Many people disagree with you about that. For example, there is a quantum eraser experiment that people believe proves that in the quantum world, data can be erased backwards in time, which makes the quantum world weird and not at all like the world of everyday experience." What would you say to that? From our point of view, the experiment does not say any of what it claims to say. From our point of view, we're following the theory of elementary waves, which says that nature follows equations that are the negative of those of quantum mechanics because particles follow zero energy waves backwards, and therefore we view it that the waves are coming from the detectors moving backwards through the equipment, and at the laser, all decisions are made by the particle as it leaves the laser. Therefore, we are looking at it from such a different perspective of Kim et al. That it's as if we were looking at a different experiment. But it's really the same experiment viewed from two drastically different sets of assumptions. So how does your picture explain anything, Jeff? In a double slit experiment, you see a wave pattern on the target screen only if you don't know which slit the particle went through. If you can figure out which slit the particle used, then magically the wave pattern on the target screen vanishes. Now, John Wheeler was pondering this thing, which is called complementarity. And Wheeler thought, well, I wonder if that would work backwards in time. Perhaps if you could inscribe a wave pattern on the target screen and then at a later time figure out which slit was used, then perhaps the wave pattern would vanish. Well, Yun-Ho Kim et al. Built an ingenious contraption which tested Wheeler's hypothesis, and they believe that they proved that Wheeler was right. Here's how they did it. A photon emitted by the laser comes across and goes through the double slits and then hits the BBO crystal, which divides that photon into two daughter photons, each of which has half of the frequency of the parent photon. So you have these two entangled photons. The upper one goes up and inscribes a wave pattern on a target screen. The lower one goes down into some complicated equipment which ascertains whether you can discover from that lower photon which slit was used or whether you cannot discover which slit was used. What they found from their data, they say, is that if there's a wave pattern on the target screen and if the lower photon does not tell you which slit was used, then the wave pattern persists. But they showed that if at a later time the lower daughter photon does reveal which slit was used, then there's no wave pattern on the target screen, and they said incorrectly that this proves that Wheeler was right. Well, that's an ingenious experiment. How do you explain what that experiment found? Let's draw a distinction between the experimenter's viewpoint and ours. The experimenters had no interest in the laser. It never appears in their diagrams, for example. They believe that all decisions in the experiment were made at the detectors. Now, they had detectors such that the target screen was closer to the laser than the other detectors, and therefore they believed that a wave pattern would be inscribed on that screen before you could discover which slit was used. We view it entirely the opposite. We claim that all decisions are made at the laser, no decisions were made at the detectors. From our point of view, the experiment starts earlier. It starts when, from each detector, an elementary wave goes backwards through the equipment, through the BBO crystal, through the double slits, and impinges on the laser. And in the laser, the photon then has a random choice to make of which of 4 different elementary waves to follow backwards. It turns out that if the wave that is chosen by the photon came from detector 3, then things are so built that no pattern will be inscribed on the target screen by the upper daughter photon. So Kim et al. Believe that depending on whether you know or don't know which slit was used, data is erased, the wave pattern is erased from the target screen. We have proved, on the other hand, that if you do know which slit was used, the equipment is so built that there never was any wave pattern on the target screen, and therefore there was nothing to erase. I mean, it's like looking at a sheet of blank paper. Would you say that that proves that data was erased because the paper is blank? It's a bit confusing. So in summary, Kim et al. Believe in wave-particle duality and have built an experiment that appears to show that data can be erased backwards in time if you know which slit a particle came through. We start with very different assumptions. According to our point of view, the data that was allegedly erased never existed in the first place. Our point of view demonstrates that there is in this experiment, there's no backwards in time cause and effect, no erasure of data, that there is no wave-particle duality. So, by explaining the quantum eraser experiment in a logical way, you have defended your idea that the quantum world is not strange, is not weird. It's like the world that we know from everyday experience. This is the end of the quantum eraser experiment. In about a month, look for another video in this series.